So we talked about what an alkane is and how to name it, and we talked about some of the physical properties. Now we're going to talk about chemical properties, which amount to what reactions do alkanes undergo. Well, alkanes are relatively inert because they just have single nonpolar covalent bonds, and there's just nothing really very exciting about them. They don't react with much. And so that makes them very good solvents because they're not going to react with the things that you're trying to dissolve into them. The two reactions of alkanes that we will talk about are reactions with oxygen and reactions with halogens. The most important thing about alkanes is that they are combustible, and so we use them for fuel. We've got a burner in the backyard that we use, one of those turkey fryer burners, and it runs on liquid propane, right, in the cylinder. And so propane is an alkane. It combusts very nicely. So when we combust alkanes, when we burn alkanes, this is an exothermic reaction. Exothermic heat going out. It releases heat energy. And you learned about combustion reactions in the prerequisite course for this class. Here we have methane. Methane reacts with oxygen. Combustion is the reaction of something with oxygen. And when hydrocarbons combust, they form carbon dioxide and water. And then they give off heat. And for this particular reaction, we get 212.8 kilocalories per mole of methane that burns. And that is definitely not a number you need to memorize. But you should know that combustion is exothermic. So, do alkanes just spontaneously burst into flame? No, they don't. Something has to get them started, but once you start it, they will keep burning until you either burn up all the fuel or until it runs out of oxygen. And so the reaction proceeds spontaneously. So if we look at methane, I'm going to draw some pictures here. Methane is CH4. So methane has 4 carbon-hydrogen bonds, right? And if we look at the products of the combustion, we get what happens to the carbon. It was in the methane, and at the end of the reaction, it's in carbon dioxide, right? So carbon dioxide is going to have carbon-oxygen double bonds. And so here, carbon has 4 bonds with hydrogen, and in carbon dioxide, it has 4 bonds with oxygen instead. Because carbon really, really likes the 4-bond thing, doesn't it? Really likes that. So combustion is an oxidation reaction. Now, organic chemists think about oxidation and reduction a little differently than inorganic chemists do. How did we observe, or how did we recognize oxidation reduction reactions in general chemistry? Does anybody remember?
Moving of electrons.
Moving of electrons. And you may have had the little phrase oil rig. Oxidation is loss of electrons, reduction is gain of electrons. And that works really well for inorganic chemistry. But now this is organic chemistry. So combustion is an oxidation reaction. It is not obvious looking at the reactant and product that electrons have moved around, right? What is obvious, though, is that we have gone from carbon attached to no oxygens to carbon with 4 bonds to oxygen. So oxidation is carbon increasing the number of bonds with oxygen. We're getting more oxygen into the molecule. So we've got those carbon-hydrogen bonds replaced by carbon-oxygen bonds. Carbon in methane is in its most reduced form, 4 single bonds, and carbon dioxide is carbon in its most oxidized form. Carbon can't do any better than 4 bonds with oxygen. So that is the most oxygen it can have. Any questions about that? So if we're comparing two molecules and trying to decide which one is more oxidized, which one has more carbon-oxygen bonds is what we're looking at. Well, what happens if you're burning an alkane fuel like propane or something and you don't have enough oxygen, like the vent on your heater is kind of blocked up, what happens?
It won't burn.
Doesn't burn very well. I know with our turkey fryer in the backyard, it doesn't seem to be very adjustable, and so it's not burning real efficiently, and it deposits soot all over the bottom of the pan, which makes a fabulous mess. So that's not good. Soot is just carbon. The real dangerous thing, though, is carbon monoxide. Carbon monoxide is carbon with a triple bond to oxygen. And you see, this is carbon with 3 bonds to oxygen. This is carbon with 4 bonds. This is not completely oxidized. And the reason you get carbon monoxide forming sometimes is because there's just not enough oxygen present. And that's why you really don't want to use the gas grill in your house. Because if it's not adjusted really well, you can kill yourself with carbon monoxide. And sadly, it happens every year. People die because of carbon monoxide. It also can generate formaldehyde and acetic acid. And you also don't want those things, being let into your house for you to breathe. So let's look at this question. Which carbon is more oxidized? In which compound is carbon more oxidized, methanol or diethyl ether? And I gave you the formulas there. So to answer this question, we probably need to draw the structures. And this is a condensed structural formula, but it's giving us clues about how things are attached. So these hydrogens are attached to the carbon before it, and this hydrogen is attached to the oxygen. So here we've got, you can't write with the pointer. You'd think I would have learned that by now. So here we have 3 hydrogens attached to carbon, and then the carbon's going to be attached to the oxygen and a hydrogen attached to that. So that's the methanol. And then over here, CH3, that's that methyl group, and CH3, a methyl group, and in between them is oxygen. So the oxygen is going to be in the middle. And so we look at this carbon. How many bonds does it have to oxygen? 1. We look at this carbon. How many bonds does it have to oxygen? 1. How many bonds does this carbon have to oxygen? 1. So each of these carbon atoms is oxidized the same because they each have 1 bond to oxygen. So the question here, in which compound is carbon more oxidized? Each of these has each carbon atom has 1 bond to oxygen, and so if you're looking at the individual carbon atoms, they're going to be the same. If you were comparing the 2 molecules as a whole, which would be more oxidized? This one, because there are 2 carbon-oxygen bonds in the entire molecule. And so the wording of the question needs to be very precise. And sometimes questions are not worded very precisely, and then it becomes confusing. So if you're not sure what a question means, especially on an exam, ask. Okay. Any questions about that one?
So it would be the diethyl ether?
The way this question is worded, in which compound is carbon more oxidized? Neither. They're the same. If we change the question, which I can do, which compound is more oxidized? Then this one's more oxidized because it has 2 carbon-oxygen bonds. I think I missed a slide there somewhere. No, maybe I didn't. So that was the reaction of alkanes with oxygen, combustion or burning. They also react with halogens. And this is called halogenation. So these types of reactions have names, and the names give us huge clues to what's going on. Oxidation is reaction with oxygen. Halogenation is reaction with a halogen. The halogens are fluorine, chlorine, bromine, iodine. They're all in the same column, in the same family in the periodic table. They behave in much the same way. And so we refer to them collectively, and we can just kind of interchange them. It's like, you know, here's two of my boys, and they both played football for Emmanuel High School. And so, you know, maybe James wasn't available to play, but we'll just stick his brother in because they're both running backs and they basically can do the same thing, right? So fluorine or chlorine or bromine, you can just kind of swap them in these equations and they'll act very much the same. So alkanes react with chlorine gas in the presence of either sunlight or heat, and that's called chlorination. So halogenation, reaction with a halogen. Chlorination is just more specific, reaction with chlorine. The chlorine substitutes for a hydrogen, and so we call this general type of a reaction a substitution reaction. So here we have R standing in for some alkyl group. It could be methyl or propyl or something, carbons and hydrogens, and there's a hydrogen on the end. And it's going to react with this chlorine molecule, and the chlorine, one of the chlorine atoms is going to take the place, is going to substitute for the hydrogen. So they're just swapping partners. It's a substitution. Okay, Zach in for James. You know, James comes out, Zach goes in. Substitution. So bromination is going to happen in a very similar way. Just change the letters here. This will be bromine, Br, and they'll swap out, and we'll end up with bromine over here and hydrogen bromide as the product. This does require some sort of energy input to make it happen. It doesn't happen spontaneously. If we have more halogen present, then more hydrogens can be replaced. And that will result in polyhalogenated products, meaning the products have more than one. Poly meaning more than one. So if you take this, what would the name of that be? Chloromethane. That is the proper IUPAC name. Oops, I forgot the M. Chloromethane. If we take that and we add more chlorine in the presence of light or heat, we can exchange chlorine for another hydrogen, and that gives us dichloromethane. And that can continue, trichloromethane, tetrachloromethane. Somebody's drumming on the wall. Which product you end up with can't be specifically controlled, but you can control it somewhat by adjusting reaction conditions in the ratio of chlorine to methane. If you have lots and lots and lots of chlorine compared to the amount of methane you originally started with, then you're more likely to end up with something like this, the CCl4. If you just have a little bit of chlorine, you're more likely to end up with the monochlorinated product. So, a word about organic equations, because organic chemists treat chemical equations a little differently. Sometimes we write a reactant formula over the arrow for convenience. So let's go back here and look at this. Cl2, that's actually one of the reactants. We're reacting Cl2 with this chloromethane to get this guy. But organic chemists just have a little different perspective on things like this. So sometimes you'll have a reactant formula over the arrow. Obvious inorganic products may be omitted. Let's go back to this one. So if one of these chlorine atoms gets added to this, and we end up with this, what happened to the hydrogen and the other chlorine? Did they disappear? No, they're still there. But the organic chemist doesn't care about them, right? We don't care about them, so we're not going to put them in the equation. These equations can get kind of complicated because we're usually having to draw structures. And so they tend to only include the things that they're actually interested in. Which if you were really on top of things in general chemistry and you got all of your equations balanced and all your formulas exactly right, this may drive you bananas. But the organic chemist doesn't care about showing all the reactants and products, only the ones that they are interested in. How convenient, right? So they may omit obvious inorganic products. The equations are frequently not balanced. They know how to balance equations, but they usually just don't care because we're not doing calculations, and so it doesn't really matter. And sometimes there are multiple possible products, and they may all be shown, even though that results in a very unbalanced equation. But again, they don't care. I am not an organic chemist. That's why I keep talking about they. I'm just trying to explain to you how I think that they think about things. So bottom line is, the equation shows what's important to the organic chemist. It's not going to show everything. I just want to let you know that because you may notice some discrepancies in the equations. When we have larger alkanes, we just looked at methane. When we have larger alkanes like hexane or something, you can get even more products just by adding one halogen, because which hydrogen is going to get substituted? You can end up with different products. So let's look at the possible products for the monobromination of pentane. Mono means what? One. Bromination means we're adding bromine. So bromination, we're going to have a bromine take the place of a hydrogen, but just one. So pentane has how many carbons? It's got 5 carbons. There's 5 carbons, and they would all have hydrogens on them. And we're going to put a bromine on there. Well, let's put the bromine on the end. And then this carbon's going to have 2 hydrogens, and this one's going to have 2, and 2, and 2, and 3. And what would the name of that guy be? One bromopentane. It's pentane with 1 bromo, and it's on the first carbon. So that's one product. What if I put the bromine on the carbon at the other end? Would that be a different compound?
Same thing.
It would be the same thing, just turned around, right? Because if we have the bromine over here, then we would have to number from this end going that way, and we'd end up with the same product. What if we put the bromine on the second carbon? Would that be different? That would be different. So let's try that one. So C, 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 C. And let's put the bromine in here. And then there'd be 3 hydrogens on the carbons at the end. These guys will have 2 hydrogens. And how many hydrogens does this carbon get? 1. So what's the name of that compound? 2-bromopentane, right? It's a little tedious at times, but a good way to identify are these the same molecule or a different molecule is by naming them. If you put the bromine at the other end of the carbon and named it correctly, you'd come up with exactly the same name, and that would alert you, oh, wait, that's the same molecule. What if we put the bromine here in the middle? Would that be different? Yeah. And what would the name of that one be? 3-bromopentane. What if we put it over here? Would that be 4-bromopentane? It would be 2-bromopentane because we'd have to number from the other end. So adding 1 bromine, there's 3 possibilities. On the 1 carbon, the 2 carbon, or the 3 carbon. If we just have the 1 bromine and add it over here on what appears to be the 4th carbon, we have to switch the numbering around, and that becomes the second carbon. So we always number to give the lowest numbers to the substituents. Any questions?
So if the number is too high, switch it around then?
Yeah, because if we have it like this, let's see, CH3, CH2, CH2, CH with the BR right here, CH3. When we go to name that, we check the numbering both ways. We go 1, 2, 3, 4. That would be 4 bromo, or if we number from the other end, 1, 2. Well, that's a lower number. That's the correct numbering then. Okay, so this guy is the same as this one. It's just turned around. Now, can you see that if you were adding 2 bromines or 3 bromines, the number of possible products just kind of explodes, doesn't it? Because if you were adding 3 bromines, they could all be on different carbons. They could be all on the one at the end. You could have 2 on this one and 1 in the middle, all kinds of different combinations.
What would be the name for that if they were all in the same way?
If you had 3 bromines, let's draw that. If we had these bromines all on this carbon, what would be the name for that? It's tribromo, right? Because there's 3 bromines, so tribromo. And then in front we have to put the number of the carbon on which each of them is. So it's 1, 1, 1, tribromopentane. So even though these numbers are all the same, we still list them all out. If we look at the cycloalkanes, cycloalkanes undergo the same sorts of reactions that the regular alkanes, the straight chains, do. So let's look at monochlorinated product of cyclohexane. So cyclohexane has 6 carbons, and monochlorination means we're adding 1 chlorine. So that will end up being 1-chloro-cyclohexane. But then let's stop and think about this. Do we really need the number 1 on there? Does this 1 really tell us anything? Do we need that to tell us where to put the chlorine? We don't. If we have a monosubstituted cycloalkane, we don't need the number because it's always going to end up being 1, and chemists don't like to write the number 1. So chlorohexane. If I put this chlorine on this carbon over here instead, is it a different compound? No, still the same thing. So for the cycloalkanes, when you halogenate them, you can get 1 product. It's harder with the acyclic ones.